Miss Jody here with our next video for Earth and Space Science. In this video, as we continue on in Chapter 10, this almost finished with Chapter 10 here, but this label is going to be our sun and other stars. So if you look in Chapter 10, you'll see where it starts talking about our sun and other stars. All right, so when we look at our sun and other stars, don't forget to be taking your notes on a half sheet of paper and labeling the back of the sheet with the title so that we can keep track of which one goes where, and we will be gluing those little sheets into our journal whenever we're able to get them back, and that way we finish up our journal. Now today with this topic there's going to be a diagram that goes along with it, and I sent you this diagram in a PDF, and the PDF has 2 pages is 1 page to print out that you can just cut in half. You can see half of it is the diagram for today and the other, or for this lesson, and the other one is for the second lesson, because we had to have 2 videos for this topic because there's so much going on here in this chapter. I can't do it all in one. So this one half will go with this, and the other half will go with the second video. All right, so the sun. So when we take a look at the sun, we've already talked a little bit when we were looking at the scope of our solar system. We started with the sun and then moved out from our planets, or from the sun, as we were following the planets. So we only took a little bit of time on the sun, just understanding what might be happening at the core. But this is going to give us a little more specific about the sun, okay? So the sun, first of all, is our star. So the sun is our star. It provides heat, light, energy. It has gravity that's going to keep us all in the planets, all in their orbital motion. And so the sun is really going to be an important source of our existence. And scientists state it as a great glowing mass of gases, mostly hydrogen and helium. And there's others, but most of the gases involved are these 2, they think. And they're heated to crazy temperatures, so extreme temperatures with the sun. And so the temperatures they give on a range from actually the surface of the sun, like touching the surface, to say around about 11,000 degrees Fahrenheit. And then all the way down to the core, the center, they're estimating, of course these are theories because we haven't really gotten to the core or anything like that, but they're estimating it to be 27 million degrees Fahrenheit, around about. That would be on average, right? So this sun is this big glowing mass of gases, superheated, and it's going to provide us with the heat, the light, and the energy, the gravity, the things that we need for life here on Earth. And the structure of the sun is unique, because when we start looking at the sun, the theory is that there's certain layers to the sun, just like when we studied the structure of the Earth, which again was also a theory. Were also theories, because what we have to do is we have to use indirect observation, meaning we can't see it ourselves, but we use observation tools to indirectly measure what we think might be at the center of the Earth or in the layers of the Earth. Same thing with the sun. It's not like we can go up there and touch it and go down into the middle of it and see what's going on. So this is going to be theories of what we think might be going on with the sun. So if we look at that, we say, okay, starting at the middle. Now, this is what the diagram is for, because it's going to start at the middle and help us go out, okay? So the middle is thought to be what we call the core, and that's where we think the fusion, which we talked about before, that's when you're fusing together the hydrogens, remember that? So the hydrogens are under so much pressure and so much intensity that they fuse together to create helium. They think that's what's going on in the core, okay? So if you look at the core on your diagram, that would be this center top here. So this is the diagram of the sun, and the center would be here. So we'd have little H's, I'm just going to put them in here, little H's being pushed together to create helium. And this is what we would call nuclear fusion. So I'm going to just put some H's in there, and then I'm going to just color this like a wild highlighter, whatever. You can use any color you want. So you can see that that would be the core. Now, what would be happening is as these hydrogens are fusing together, we talked about this before, they fuse together and become helium, and in that process a lot of energy is released. And when that energy is released, it's trying to get out, and that energy, it's so densely packed. So what densely packed means is that there's a whole bunch of molecules in an area of the gases, and so much packed into an area that this energy has to go through all of that to try to get out. And eventually we see this process. It's kind of like boiling water. If you think of boiling water and you start to boil it, after a while you start seeing these bubbles rising to the top and popping out. So think of that in the sense of the energy. So the energy is going to want to come out as these hydrogens are fusing together. It's going to want to escape, but it's got to move through all of this to be able to get out. So it takes it a long time, so the theories say, for it to get out of this particular area. Now this area, and I'm going to highlight this the same color, the core, which we were just talking about, that center part, and is estimated to be about 27 million degrees Fahrenheit. And I'm also going to highlight in the same color the radiation zone, because that's going to be this part of it where the energy is trying to get out. And I'm going to put them, some scientists put them together and say they're part of that same system, some don't, but I'm going to put them in the same color so you know they kind of go together in a sense. My highlighter is seeming like it's running out a little bit here. And so in that radiation zone here, I'm going to change this yellow here. We got all this energy trying to get out because of all this nuclear fusion going on in the center, okay? So these two are going to be of the same in thought, okay? The core and the radiation zone. Now the radiation zone, as that energy is coming out, then, oh, and it does show you here ray of light. So I'm going to put that the same color too. So that one, see these little ray of light. So as the energy is coming out, and these little pockets of energy that we call photons in our theories are trying to make their way out, and that's the process of the light that we normally see, the visible light, and even the light that's not visible, even that will be trying to be escaping in this process. And so when we look at that core, we got three main things happening there on our diagram. Pushing together the fusion, we've got the radiation zone, it's trying to get out from the center, because like I said originally, this whole sun is thought to be this big ball of gases. So it's a bunch of gases that are being pulled towards the center, which is creating that pressure there, but as it fuses together, that energy wants to escape through all the gas, that big ball of gas. So we have that first area, the core, the radiation zone, and then that ray of light coming out of there. So if we go back to the note page here, we have the core. So the core, the radiation zone, and the convection zone. And I can do this, you don't have to, but I can do this to try to remember what color I put them over there, so I can kind of keep track of these going together. Oh, I don't want to put the convection zone. I'm sorry, I don't put that one yet. So, because that's the ray of light. That's what I should highlight there. That's the ray of light. What they're trying to come out, and all that energy trying to escape, right? So this would be that nuclear fusion. The H is being pushed together to create the helium. The hydrogen pushed together to create the helium, and the light coming off of that, and that process we call fusion. So that would be the start of it, okay? Then we'd have another area, and if you go back to the diagram, this would be the convection zone. And I'm going to change colors on this just so we can keep track of it, okay? So I'm going to make the convection zone this orange, okay? The convection zone is this area where it's going to start bubbling, sort of, in a sense, creating these convection currents, just like when we studied the Earth and our atmosphere, and we looked at like the weather and how it creates these Hadley cells. Do you remember them? On the outside of the Earth, it kind of creates these circular motion of really warm air rising and then cooling off and sinking down and creating these circle patterns. Well, this is what that's similar to. It's these convection currents where the air, not the air, actually the gases, because this is not gonna, the sun is not gonna be a ball of air, because air is a mixture. What we call air would be our mixture of 78% nitrogen, around 21% oxygen, and then less than 1% of other gases. So that would be our air mixture. So this would be just kind of a gases that wouldn't be the same as our air. You could maybe still call it air, but it wouldn't be our air. Okay, and so these gases they're really, really heated up, and they're starting to move in these patterns as they get really hot and try to bubble out, and then they get cooled off and they sink back down and bubble out and sink back down. And in this process of this convection zone is where we have the layer that we talk about when we start layering beyond the gases, what we call the atmosphere of the sun, and that would be the photosphere, would be that first layer. Now I wrote photosphere over here. I also have it on the other page, but just because I'm over here, I wrote it photosphere, and that means sphere of light. So it's the air, it's a sphere of what when we would look at the sun, which you never do, of course, right? You would never look at the sun because of the intensity of that energy coming off of it. And so with the photosphere, but if we did look at it through a special telescope where it wouldn't be damaging to our eyes, then that's what we'd call that sphere of light. It'd be like what we see, the bubbling side of the surface of the sun. Now that sphere of light is thought to be the top of the, right above the convection zone. Now, some scientists put the convection zone and the photosphere together, so it kind of gets confusing. That's why I'm just going to color them in groups, okay? So the core and the radiation zone and this light coming out, I'm going to make that a group of kind of an area of the sun. And then the convection zone and the photosphere, I'm going to make that kind of an area. And so for the photosphere, I'm going to still do these little dots out here with the orange. So you know that it's also like a layer right at the top. So remember when we studied our atmosphere, and the atmosphere was the sphere of the air that was around our Earth and kind of laying on us? Remember we had blankets. We would call them blankets of air because they were layered, and we had 5 different layers of our atmosphere, and we were able to figure out those layers, and in each layer it had a different properties. Some of it was really dense and some of it was spread out, and you had different temperatures. Well, that's the same thing with the theories of the sun. The theories of the sun is there's still something surrounding it like a blanket. And they still call it atmosphere. So like the air sphere, but you just have to remember it's not the same air as what we have around us in our atmosphere. Okay, so this atmosphere, this air sphere, this gas sphere that's around, that's that first layer, the photosphere. So if I go back here trying to keep track of my layering, I got my yellow ones, which is the core and the radiation zone, and then combining together, just to keep it simple, the convection zone, that's where those currents are being made of the rising up of the hot and then the cooling off and sinking, and it starts making these currents. And the photosphere, which would be that layer of that first part of the air or the atmosphere around the sun, and that is also an area where we'd see the bubbles and the sunspots. And so if we look at the diagram, I wrote it over here, and you don't have to, but just to keep track of it, I did. Granules, okay, granules are little bubbles. Well, I shouldn't say little because they're not little at all. What they are is they're big, wide, like 600 miles across of these bubblings. Again, just think of it like a bubbling water boiling, how it keeps making these bubbles and popping out and popping out. Just think of the surface of the sun like a boiling hotness, and it would just make these bubbles, but these would be giant bubbles. And so these bubbles about 600 miles across, and the book says that's a little bit bigger than the state of Texas. So these are some big bubbles on the surface of the sun. But then there's also super granules, and these will be bubbles that some of them are so big and they last longer than the bubbling of the little granules. The big super granules would be about 22,000 miles across. So that's super big compared to 600 miles across. So the first one's only 600 miles across. This one's 22,000 miles across. So these are some super bubbles, right? So at the surface of the sun, because of all this hot coming up, this heated gas coming up and then cooling off a little bit and then sinking down and then coming up and bubbling, you start getting these bubbles in that photosphere. And so I'm going to try with my little dots to kind of make bubbly looking dots. So we have these granules along with just the sphere of the photosphere itself. We got all these bubbles bubbling up, and it's just getting a crazy mess right here on the sun. And so I'm going to put all those together with the orange so we can keep that straight. And then if we Oh, and I guess I should put this little word, hot gas rising, because that was going on with the orange area. The hot gas was rising. And the cool gas sinking down. That's those convections areas, the areas where it's making a circle in a sense, where it's rising up and then cooling down, rising up and then cooling down. And it would be nice if I use a little red actually, because on these little circles, if I make some of it a little red going up, then that's hotter. That kind of red looks like a pink. Let me see. Let me use one of my grading pens. So if I did this, then that's making it look more red. Well, this one's not too red either. I don't know if I can let me see if I have a dark red colored pencil. Sometimes you can really push down with the colored pencils. Here's one. Let's see. And that will still go along with the orange, but see how I'm making a little bit darker red? And that's going to represent where it's getting really, really hot as it's coming up, but then it cools down and goes back down orange. So orange and red, just to remember it's kind of cooling down. Still hot, that's why it's still orange, but it's really hot as it's getting all heated up by this energy trying to escape, and then all of the bubbling that's happening here. It's getting really hot and then sinking back down, and so that might help a little bit to understand the pattern of getting really hot and coming up to the top and bubbling and then cooling off and then sinking back down and coming up, okay? So this could be really a good visual for us to be able to see what's happening in this bubbling sense of the sun. Now, when we see this happening in this first layer, and the bubbling, we think, well, is that it? We just got that photosphere. But then there's another sphere, another part of that atmosphere, another layer. Now, remember when we talked about our atmosphere, we had 5 layers. This is really going to only be the photosphere, the chromosphere, and the corona. So they're going to have really like 3 main layers around the sun. So it's not as hard to memorize than when we were studying our atmosphere. So you got the photosphere. This is, of course, spheres around after we get to the core. So the first sphere is the photosphere, and then the chromosphere is the sphere of color. And they say sometimes it's kind of like a pinkish, depending on how you can view it. Let me see if I have a good pink color. I have my marker bucket here that will help me. Let me get a pink one. Hopefully I can find one that works well. All right, and so I'm going to put the chromosphere, this one right here. I'm going to kind of make it like pink. The sphere of color, you would actually have to like use something to block this part out. Now this is my glitter I'm going to use later, but you'd have to have a telescope that's blocking this part out for you to see any of this outside, because it's so brilliant and so bright that if you just looked at it, it just looks like a burning ball of gas, right? It's so bright you can't really see the sphere around it. You need a special tool to be able to see that. But if you did, you would then see that layer. Now, some scientists will say that this is the lowest layer of the sun's atmosphere, and our book said that, but then some books say the photosphere is also the layer. Some people say no, the photosphere is just the bubbling, it's actually the surface of it, and so it's kind of hard to figure out which one is which, and so in different opinions there. So I'm just going to make it that it's part of this where the orange is too, in case it ends up being that it's the main lower level of the atmosphere, and then we would have just the photosphere be the actual touching there, the actual surface where the convection currents are. So who knows, right? So, but I'm going to put this pink layer in too, okay? So this pink layer, which will be the chromosphere, is said to be the lowest layer of the sun's atmosphere, and in that we're going to have a few things happening in this lowest layer. One, we're going to have what we call spicules. Spicules are kind of like these bursts, and I'm going to try to draw them in with pink, but you have to remember these would be flame-like columns of gas. So even though it's pink, I'm going to just kind of draw them as little lines. Now the reason we draw them as little lines because they're columns of gas that are in that pink layer, and that pink layer can help us see with these spicules and other things that this is going to be a pretty violent active layer of atmosphere. And so I'm going to do that there with these spicules. Now I drew them all the way around, and I did that because in the book it talks about how these spicules sometimes, because they look like blades of grass coming off the sun. And if you've ever drawn the sun, you know how you draw the little rays coming off? That could represent the rays trying to get out, but that can also represent the spicules or the other things that are flying off in that situation. So these big columns of gas, some of them they say are like 600 feet across and 6,000 feet high. I mean, would that be crazy, right? That would be pretty high, these spitting flame-like columns of gas. And when people look at them, they say they look like blades of grass, and they call them the burning prairie. So imagine just a big grassland on fire, all these little pieces of grass. That's what they're saying it looks like. And in some areas, they can even be higher and longer. And so you got these columns of gas, and that's what we call the spicules. And I put those here. Spicules. And then the solar flares are also something we see in this pink layer. And the solar flares are going to be like these big, tremendous bursts of energy. And they think they're caused by the magnetic stress. And so with the magnetic stress of the way that the magnetism of the sun and all the gases moving around, creating all this pull between positives and negatives, can create a stressful situation that sometimes we have big bursts of energy that comes from these breaks in the magnetic crossing over. And so I don't know how I'm going to draw a solar flare. I guess, well, what would be good is for me to also explain solar prominences. And I wrote these on the other page too, but I just have them over here on the diagram. But I have them on the other page for you to write too, so if you can't see that very big. And of course, young ones, don't forget, you don't have to write all these notes. This is just, you just fill out the diagram with me, okay, as we go along with your colors. All right, the solar prominences might be easier to explain them because they're kind of like these streams of dense gases. So instead of a column, they're kind of like streams, and they return in a loop. So they kind of come up and they return in a loop like this. Okay, so once they return in a loop and they're not kind of broke, and they still think they're part of this magnetic situation, the magnetic stress and the magnetic field of the in this particular area. And so, but they loop over and they don't disconnect, okay? But when it comes to the solar flare, sometimes it's these two crossing over and then it breaking, and then we've got the solar flare going off. And the solar flare, this big burst of energy, causing a bunch of things to fly off in that pink area. And when that happens, there's streams of atomic particles that will fly off, and what will happen is it will fly and then it will hit the earth. And when it hits the earth, good thing we have the magnetosphere. Remember, we studied that way back in the earth time. And actually, I was able to just pop it open to this page. How great is that? Remember this little magnet thing that we had created with the magnetosphere around? And we used a magnet to move these little things stuck in here. Remember that wonderful magnetosphere that's helping protect us from all these waves of all these particles? And this was my terrible rendition of the magnetosphere. And of course, even worse is my distance between my sun. This is supposed to be my sun over here, and my big magnet sphere. So here I had all these these particles flying at the sun, flying at the earth. And of course, this is supposed to be approximately 93 million miles away. But I got it a little close there, right? And so this is not a great to scale illustration, but it's an illustration just to show the importance of the magnetosphere as these particles are coming at the earth. And because we have this wonderful sphere of magnet influence, then some of them are going to move beyond and not go directly at the earth. But remember, we talked about some will get into the tops and the bottoms, and when they get into the tops and the bottoms, they create those beautiful auroras. And I don't know if we didn't have time to do the auroras on here. You guys might have in your book, and maybe I didn't in mine, but I'm just going to draw in some beautiful auroras here. I just happen to have blue, so I'm just going to do blue. But remember the different colors, the red. Oh, I actually have a red too. The red colors of the auroras, the greens, and that would be depending on when all these little particles would start flying and hitting the atmosphere, and at the tops and the bottoms creating these wonderful auroras. But you remember that magnetosphere, how important that magnetosphere was into protecting the Earth? And so when we think about that with the sun, all of this stuff flying off the sun that we're illustrating here in the pink in these solar flares is going to be it's going to be good that we have that magnetosphere to help us from things that are coming. Because what happens when we do have a solar flare, it can really mess up things. Like on Earth, if we have too many particles coming into our atmosphere and getting in the tops and the bottoms, that can mess up with our radio communications. We can have all kinds of like electrical power outages and stuff. And so sometimes you'll hear them talk about this in the letter CME, if you've ever heard, coronal ejection, CME, yeah, coronal mass ejection. And so between what's flying out in the chromosphere and then also the next layer, which is going to be the corona, then that's also an area where we're talking about this problem with this stuff flying off the sun. Okay, so just to recap there, we've got those solar prominences. They're kind of arcing back and forth, and then there's sometimes a stress in the situation, and then flying off the particles. I did miss one here, sunspots. I got to put sunspots back in my orange. Yes, my orange, my sunspots. I wrote the definition over here of sunspots. These are dark patches caused by the sun's magnetic field. They're cooler and they follow a certain cycle. And by tracking the sunspots, so they'd be kind of at the surface here in the orange, these different sunspots that we see. And actually it would have to be a little darker orange. I'd probably have to kind of create them in more of a red. That is what we see on the sun on the outside when we're looking at it, and there's like a little pattern, and that's what helped us understand that the sun was actually rotating itself. And so the sun was rotating on its axis. And whenever we always thought the stars stood still, and they do in a sense, that in our pattern they're not orbiting us, they're staying still, and then we're going around the star. But the star actually is thought to now actually be spinning, and so rotating, staying here but rotating and spinning. And so tracking those sunspots has helped us understand that. Okay, so the sunspots were part of this orange area, the granules, the supergranules, trying to keep track of all these crazy words since I had to write them all over the place. All right, and going back to this page, now the chromosphere, when I did in the pink, I'm going to box this in the pink so I can keep track of it. And that's where the spicules, the big columns of gas, or the solar flares where they snap out and particles go flying, or the solar prominences where they arc up. All of these will be in that link to that area, scientists say. And then there's a next area, which we would call the transitional region. And I'm just going to do that in gray because I'm going to think of it as like transition area. It's a very thin. And also it's where they think that a lot of the UV light is produced, and that would be the ultraviolet light, the part of the light spectrum that's not visible to us unless we have special circumstances to see that. And so that's pretty damaging light, but thankfully we have a lot of ways that it's blocked from what gets into the earth. Past all of the boundaries, we have the ozone layer that helps break apart UV light, and so that can be some trouble spots, the UV that's created, they think, in that transition area. So with that gray, it's not illustrated on here, but I'm just going to do like some little dots here of gray to try to remember that little thin layer transition area of the UV. And I might even do this little like things coming off here, the UV light, just to try to remember that. Okay, and the little gray, little UVs. And then we have the next layer, which would be another main layer, and that would be the corona, which you're normally used to hearing. And that's an ever-changing area, and that sometimes you can see when, like we said before, that if something goes in front of it, like on your telescopes, or if you have an eclipse and something goes in front of the sun, then you're able to see all of this outside stuff way better, which is nice. Now I'm trying to figure out which color am I going to use for the corona, because I've been already gotten a lot of colors used there. Orange, pink, nothing too, I guess. If I had a better highlighter, I would use that one. Let me see if I can grab a better highlighter up here on the counter. All right, here's one that'll be hopefully better than that. That way we have a really bright color for the highlighter for the outside, which we normally think of the corona. So I'm gonna like do this out here just for us to think of like that out layer. And the reason it's called corona is because it makes it seems to look as if it's a crown, and that's what the word corona means. Now you have to just keep track over here that it's a little bit lighter color yellow than this yellow from the core area. So I know that's really confusing, a lot of things to keep track of there, but just for us to understand the composition of what the scientists think the sun, how it's sort of all put together in its layers. Let me put this corona in the light color here. Now this is an area where it's ever changing, and there's like lots of holes, they call them, that are created in this little last layer of the atmosphere. And this is also where they say the solar winds are concentrated and coming from. And the solar winds, they are really super high speed streams of particles ejected from the sun. So we've got our regular particles, and then we got these super high speed solar winds, and they also are moving towards the earth. And we also have that wonderful magnetosphere to help us with some of those situations too. Now, if we review, the core was just the middle of it, right? What's happening, where all the action is happening with making what needs to be made, in the sense of that nuclear fusion and getting that energy out. And then we had this area, the convection zone and the photosphere, and that was that bubbling stuff and the sunspots, the actual surface. But then some people say this is also a layer of the atmosphere, and some people say no, this is actually the touching of the sun, the actual surface in this area. And then the chromosphere, which could be the first layer of the atmosphere, unless you think this is the first layer of the atmosphere, that there's a layer there too. But with the chromosphere, that's where we have the spicules and the solar flares and the solar prominences. And then we have that transition layer, and that's just gray, so you can just think of it as a splitting there. And then we have the corona, which is the ever-changing layer that's totally at the outside and where we have the solar winds. Okay, and so that's our sun. And then when we look at our sun, we also have to say our sun can be an example for other stars, but it doesn't mean just because our sun structure is like this doesn't mean other star structures are going to be like that. And so it all depends on the way that it's all put together and what that star involves. So with the other stars, the only main things we want to focus on, and there's a lot in the book, but I want to just focus on a couple things. One, the apparent magnitude. So when we start looking at stars, we have what's called the apparent magnitude. And what this means is like how the star appears from Earth. So your apparent magnitude, like from me, how do I look at the star and how bright does it seem? How's its magnitude? And so we had a scale like back in the day when they first started this scale, and we kind of keep it similar, but it was from 1 to 6 back then. So 1 being the brightest stars, and then 6 being like the faintest. So just think of it this way, 6 being farther away, and that in the original thinking, but that's not really how it works. But just think of white, 1 is closer to you, 6 is farther away. So the ones that are brightest, the idea was that they were the brightest, think of it closer, and then the faintest as the 6. But it's really about how bright, whether it's close to you or not. And so we still kind of use this scale, but we have to go, now that we have a little more understanding, we have to go lower than 1. And so we have things like Sirius, that set of stars is a 1.5 in the apparent magnitude. Our sun, which is not really super bright compared to other stars, but compared to us standing on Earth looking at, would be like a negative 27. Like it's really, really, really bright because we're standing on Earth. So the apparent magnitude is how you appear it from, how it appears from Earth. Okay. Or if it's really, really, really dim, our scale over here can even go all the way to like 30. And that's things we can barely see from Earth. Again, apparent magnitude is from Earth. And then you have what's called absolute magnitude. Now, the absolute magnitude is the apparent magnitude that the star would have to an observer if the observer was 32.6 light years away. Now, if you have not studied light years is all about how far light can get in 1 year, which is very far. It can travel very far in 1 year because light travels so fast. It's so super fast. And it's what, 186,000 miles per second, something like that. And so it's going so fast. So imagine if you're driving to Florida and it takes you 1,500 miles to get there, and you're driving 60 or 70 miles an hour, and you feel like it's going to take you like 15 to 18 hours to get there. Driving to Florida. But if you were going the speed of light, it would be nothing because the light travels so fast. In 1 second, you could go 186,000 miles. So you could be like to Florida and back 17,000 times. No, not quite, but you see what I'm saying. So if you could travel the speed of light, it'd be really fast. So 32.6 light years means how far can light go in 32 years? Well, if it can go that far, 186,000 miles in a second, could you imagine how far it can go in a year? And so this is a far distance. So if you were from a far distance looking at this star, what would your magnitude be? So that would be your absolute magnitude. It would be from that 32.6 light years away. And so we would have to figure that out. Like our sun, if we were 32.6 light years away, our sun would be a 4.8. Our sun would not be over here at negative 27, like really bright. He would kind of look dim. He'd be on this side, the 4s, 4, 5, 6. He'd be far out because he'd look dim if we were that far away. So you have the apparent magnitude, how it appears from the Earth, and then the absolute magnitude, how it would appear if we were really, really far away, 32.6 light years away. All right, so temperature and color is another thing that we look at for other stars. And when we look at these temperatures, and I tried to illustrate them down here, if we have more of a reddish orangish, this is going to be around 5,000 degrees Fahrenheit, we think. So we look at some of these orange stars or red stars, then we're thinking, oh, it's kind of not too hot, right? And then more of the yellow stars, which this was where our star would be, because ours at the surface is thought to be about 11,000 degrees Fahrenheit. So we'd be kind of in this category, these yellow guys, around 10,000 or so degrees. And then the white star, and I made it the highlighter because I couldn't, I don't know how I was going to do white, but this would be kind of whitish and actually whitish bluish. So why don't I mean, heading towards a little bit of bluish. So what if I put a little bit of this on here just to kind of illustrate heading towards blue. So these guys, they're really white, and I actually have a white crayon. So with that little blue glimmer, if I put a little of that white over it, I might be able to make this look a little more whiter. And so with this bright star, the whiter looking ones are thought to be around 20,000 degrees Fahrenheit. And then when you get up into the bluish colors, they're the really hot, thought to be around 40,000 degrees Fahrenheit. So at the surface. So our colors can help us see the temperature of the different stars. Now with the temperature and the color of the stars, that leads us to the Hertzsprung-Russell diagram, which is normally just illustrated as the HR diagram because it's hard to remember the name there, Hertzsprung-Russell, the gentleman involved in creating this diagram. But this diagram right here, so I printed this out for you, is just a diagram of tracking these stars and kind of keeping, making a graph of them. On this side is a luminosity, like how the brightness side of this star here, and then this part is going to be, excuse me, the temperature side, how hot we're going to get. And so down here it's lower, and then it gets hotter as we move this way. 5,000, 10,000, 20,000, 40,000. So I probably should have did my colors opposite. Should have probably put blue here, then white, then yellow, then red to keep it track on how this chart went, but didn't notice that. So when we look at the temperatures, we start to be able to put them on a chart here. We have a couple areas that kind of, with the how hot it is and then how bright it is. The chart can lead us to certain little areas where these stars can exist. And so we have over here with lower temperature and our brightness here, let's see, I can barely read this, but negative 10 to the negative 4, 10 to the negative 3, I think, and then 1, 10 to 2, 10 to 4, 10 to, you can hardly tell on that luminosity there, but obviously brighter, depending on like the mass too. So your brightness can depend on how big you are also, along with how hot you are. So these big red supergiants, they're kind of bright in this scale, but it's because they're so big. If you would be smaller and you'd be a red guy, which would be a lower temperature, you would have less brightness. But it's because you're smaller, you don't have as much mass. But if you're all the way up here, you see this scale, all the way up here, you're gonna have more brightness. And then this would be less brightness down here. But your temperature, you're in this temperature zone. And then the warmer you get, then we can start seeing the other ones here. And I didn't finish this diagram here because these guys are supposed to be orangish. Must not have had an orange. And I had these more red, and these would be some of the orange ones here. So it starts to create this pattern so we can keep track of them. In this category, the red giants or the red supergiants, the bigger, more massive, having more brightness. And then these are still cooler, like these, larger up here and cooler, and these are like not super large, medium large and cooler, and then these would be really small ones and cooler. And then once we get to the middle, that would be the average, which would be where our star is in some of the yellows, the real yellows, and then heading towards the white. I'll just do a couple yellow. So our sun would be in this. And this area right here we'll call the main sequence. The main sequence of all the stars where they're sort of fitting in. And of course, that is temperature and then how bright they are. But of course, some of these that are really big, they end up being brighter because of how big they are, and they're way up here. But the majority in that main sequence there, depending on the size, the warmer you get, the brighter you're getting, right? And you're going up a little bit. And so then if we keep going up and we get warmer and warmer, we're starting to get blue guys up here. So they're going to be brighter because they're warmer. And also these few right here would be like the white ones. I'm gonna try to put these, it's hard with the little white crayon. So that would be some of those. And then really blue, as the farther we get up and the more temperature that we have, then the more brightness there. We also have, so we have this little red, or the red giants, the red supergiants over here. Also the blue giants. These are the ones that are really hot and they're also big. But they're smaller in a sense than some of these guys, but they're giants for the blue world, right? And then we have the white dwarfs. These are really small and they're very hot and a little dim. See how they're down on the dimmer side? And so then when we look at this chart, it helps us keep track of who would be, depending on your temperature, how bright you'd be in which area you would land. So the red giants and the red supergiants, the main sequence here of the increasing in temperature, increasing in luminosity, and then of course a little category of the blue giants over here, and the little category of the white dwarfs down here that are a little dim, still hot, very hot. They're on the hot scale, but they're dim. Okay, so that little chart keeps track of all of our stars for us and trying to figure them out. That Hertzsprung-Russell diagram. All right, so with this, if you want, I have a little bit of glitter, so I'm going to add a tad bit of glitter to my sun diagram, and this is not something you have to do, but if you did have something you're getting bored of having, just doing notes and not going to do too many of our projects, and of course if your parents allow you to have glitter. I have a glitter addiction, we all know that. I'm just going to put a little extra little glitter on the outside here of this Corona so I can remember that. I have these little guys And I really haven't got to play with glitter in a while, so I miss all of our class time together and get to do our fun stuff like this, because that's how it always sticks in my mind, and I just love that creativity. So I'm going to add that little bit of glitter in there, and I'm going to shake it off in a little pan. But again, you don't have to add that to your diagram, just your colors are just fine. But that will make my little diagram a little sparkly, which I will like a lot. All right, so that ends our sun and the other stars label, and then I'm going to do a separate video for the second label that we have to do to finish out this chapter.